If you're just joining us, you can type in the chat. Let us know where you're joining from, and we'll get started here shortly.
What if the cleanest fuel on Earth could lift a helicopter, power a data center, and protect a nation all at once? At HYSKY Society, we're turning that question into reality. Our mission is to connect the pioneers using hydrogen to solve the world's hardest energy problems, whether that's flying further, powering AI, or reaching the front lines. We do this through key programs like HYSKY Monthly, where we highlight global experts in hydrogen flight, and Flying High, the top hydrogen aviation event, or HYSKY EDU, with courses like hydrogen aircraft design, and HYSKY Connect, a fast-growing platform linking hundreds of hydrogen innovators. At HYSKY Society, we believe in clean energy abundance, and hydrogen, the most abundant molecule in the universe, is key to unlocking it. So, we're sharing this pivotal research in order to deploy these innovative technologies across the world. Think aircraft that fly hundreds of miles with zero emissions. Think clean energy for AI data centers. Think drones with the range to reach targets far behind the front line. Hydrogen isn't theoretical. It's happening now, and HYSKY Society is where it all comes together. Welcome to HYSKY.
Good morning, afternoon, and evening, everyone. Thank you so much for joining us on this nice August day. So today we're doing something a little bit different, trying something new, and we have three amazing speakers for you. So we won't hear from the speakers for as long as we typically do, but it should be packed with great information. So first, just some housekeeping. This is recorded. Please keep your microphone and camera off until the Q&A section, and then you can ask your questions and answers. And let's save the questions until the end of each speaker's presentation. So there'll be a Q&A. So first we'll hear from Dennis, and then we will have a Q&A with Dennis. Then we'll hear from PJ, and then we'll have a Q&A from PJ, and then we'll hear from Diego, and then we'll have a Q&A with Diego. So without further ado, I am so excited to introduce you to Dennis. Dennis graduated in mathematics at the University of Padua. His first job was the development of custom mathematical models for the simulation of HVAC units and a software used to design innovative cooling equipment for data centers. Together with three colleagues with a background in aerospace engineering, he founded Novaeka in 2017. The original idea behind the new company was to provide engineering services to the industry at large, transferring techniques, practices, and methodologies from the aerospace industry. In the first couple of years, Dennis worked on CFD simulations for underwater autonomous vehicles, 6 degrees of freedom dynamical models of flying objects, models for HVAC units, custom software for scientific computing. Everything changed in 2019 when Avio, the Italian aerospace company manufacturing the Vega launcher, chose Novaeka to design its space propulsion test facility in Sardinia, a test bench for 100 knots LOX LCH4 engine with scale up potential to 1,000 knots. Thanks to this experience, the company specialized in the design and later on the construction of test facilities for rocket engines, successfully designing up until now 10 facilities across Italy, France, and Spain. Ladies and gentlemen, please welcome Dennis Scaggiante to the stage. Dennis, the floor is all yours.
Hi, Danielle. Thanks for the introduction. So let me share my screen with my presentation. Uh, Here we go. So the topic of my talk would be from rocket testing to basically testing special components for aviation. And I'm gonna talk a lot about space in this talk here because it's what we do primarily. So for a long time, access to space was just for governments doing scientific research with taxpayers' money. The main objective of sending staff or people into space was the exploration of other planets and doing scientific discoveries. So basically, up to 20 years ago, the space economy was very limited and almost exclusively dominated by governments. Governments gave contracts to private contractors to develop technologies that then were used by governments themselves. In this context, it's only natural that there were just a few very expensive launchers, launch vehicles, and each one was essentially controlled by a different government. The launches were very sporadic, very expensive, and the payload was almost always of scientific nature. Everything changed when companies like SpaceX proved that it was possible to dramatically reduce the launch cost, thus opening the opportunity for using space for commercial applications. The commercialization of space has led to an exponential increase in the number of satellites that are put into orbit and an exponential service in launch service demand. For this reason, the landscape of launch services has diversified a lot, and private companies have started to develop new concepts like reusability, for example, and really make a lot of different launchers, different in size, different in mission, different in application. And with this great deal about launchers, what is the most difficult part to manufacture, to design a launcher? It's the propulsion system. The principle behind a rocket engine is pretty simple, to be fair, but the reality, the devil is in the details. So the reality is very, very difficult. The physics that takes place inside an engine is so complicated, non-linear, extreme that all the simulations in the world cannot replace the value of real life data. So testing a rocket engine is absolutely a priority, but it is a major roadblock. So there are basically two ways you can go to tackle this problem. One way is just investing the money required to build your own proprietary test infrastructure. This is often difficult for the, let's say, new space startups to justify to their investors and can be a serious challenge. Imagine you have a team that is very focused on developing a very complex product like an engine, and all of a sudden you want to do real tests, so you have to invest time and money to develop a completely different system, that is the testing system, and so you have to defocus your activities and face lead times up to 18 months to get a facility, let's say, from design to commissioning to up and running. And so it's a serious bottleneck. The other way, of course, is outsourcing. There's plenty of institutions that provide high quality testing services. You have NASA in the US, we have DLR in Europe, and they work perfectly for maybe final acceptance testing or qualification testing, but they suffer a lot from these problems. The first one is low availability. If you are lucky, you can get maybe a couple of testing months per year, at least here in Europe. So, and this is way less than needed, especially during the design phase of an engine. The second problem is export control constraints. For example, if I wanted to test my engine in the US, I ship the engine to the US, but then don't give it back. So this is one problem. And the last problem is the cost. After maybe 1 year of testing in outsourcing way, basically you have spent as much money as you would have spent if you have just founded and bought your own test facility. So here we come into the play. Our company has a long experience, as Danielle already mentioned, in designing and building testing facilities for rocket engines, and also fluidic ground means for fueling launchers. We have worked on 10 facilities in Italy, France, and Spain. And for 3 of them, we have acted as prime contractors for the design. So taking care basically of all the design aspects, not only the fluidic system, that is our core capabilities, but also the civil works, the electrical engineering, data acquisition, and so on. For 2 of them, we have acted also as general contractors for the constructions. So we have taking the responsibility of delivering the finished product to the client. And we have also worked with systems for fueling launchers with cryogenic fluids. We have a good track record, and we have facts to show it. So I'd like to show this little video of Avio. This test here is from a 100 kilonewton liquid oxygen, liquid methane engine, and it was tested in this facility that you see, and that was designed by us in 2019 and 2020. So it's pretty cool to see it working, and it's pretty cool to see that the work that we do actually ends up doing a real impact. So up until now, we have always focused and worked on specific requirements from each client. They give us requirements, we formulate a design, they review and customize it, and the facility gets built and done. However, after doing 10 of them, we have understood that there is a lot of space for standardization, and this could lead to a lot of cost saving. If you think about it, all launchers or engines share a few basic requirements. They need a certain amount of fuel, at a certain flow rate and a certain pressure. And all of these basic functions can be standardized and made modular. Another great thing with portability, if you are designing and building a small engine, it would be ideal to be able to perform the final test before the integration into the launcher, and to use the very same equipment that you used for the development and acceptance testing. If instead you are building a launcher, it will be very nice to be, let's say, spaceport independent. So being able to launch from every spaceport that there is out there around the world, and you could take your equipment with you to refuel your launcher. Putting all of these together, this is our solution, at least the idea we have, a portable modular fluidic subsystem that can be assembled to create a complete testing facility, as shown here in the slide, or with minor modifications, a fueling system for launches. The idea is to transform something that now is really time consuming, expensive to have, into something that is almost a off the shelf component. And we are working on this. We have two potential clients in Europe. One is an engine manufacturer, and one is a launch manufacturer. And we have also one potential client in the US. So finally, we come to hydrogen. I didn't mention hydrogen anywhere so far, but the idea is very simple. Do the same thing for hydrogen. So developing valves, pumps, or other kinds of fluidic equipment for liquid hydrogen or gaseous nitrogen requires a lot of testing. The scale of these tests is probably much smaller than we are used for the engines. So that's for the better, because usually it becomes less costly. And the idea is the same. So have a portable and modular testing equipment for performing tests on liquid hydrogen or gaseous hydrogen components. We are actually already working on something like this, and the render there is exactly the system we are working on for an Italian institution. So share your needs. If you have troubles with testing, and if you want to share with us some high-level requirements, maybe we could already have something that saves you a lot of time and a lot of money. So thanks. And if you, of course, if you wanna go ahead with the Q&A, I
Yes.
finished a little bit early.
No worries. I'm sorry I took a minute to come on because the toolbar was hidden. I couldn't find it.
Okay.
Um, yeah, but this is a great time to ask Dennis your questions. You can turn on your camera and ask him directly, or you can put them in the chat. But we always encourage people to turn on their camera and go ahead and ask them. It looks like, Sarah, you have a comment. I don't know if that was with
It was,
respect.
you know, it was
Yeah.
not in reference to the presentation, so I let folks with questions for the presenter to ask them.
Okay, Doug, I saw you first. Go
Yeah.
ahead and ask your question.
Well, I came in a little late, but I wanted to ask, is this fluid test system sort of one of the systems for a static test stand? If you had a rocket motor, am I getting this
Mhm.
right? You're going to just test the fluid systems for supporting a rocket
It's
motor, but
yeah, it's for hot
yeah.
firing also. So basically,
Oh,
as I
really?
showed in
You
the
can.
video,
Oh, okay.
it's everything from proof testing. So basically, you put the components of the engine under pressure and you just check they don't blow up. But it's up to the testing of the engine, even with ignition and
Oh,
fire.
so there's a force balance system installed on it so you can measure things. Okay,
Yeah.
that's what I was just wondering about as you were going through your lecture. I had problems getting into the link today. I apologize. I was 6 minutes late here. So thank you. Thank you for your answer. It's clear.
Thanks.
Joe, I see you next. Thank you for the question, Doug. Great question.
I'm sorry. I think I missed what you asked us to do because I came in late.
Okay.
Well, we
The-
were
the-
just,
Oh boy.
I told people to turn their camera on or unmute if they had a question for Dennis. I'm assuming you don't have a question.
Right. So turn off my camera.
Yes.
Okay, because you always tell me to turn it on. Okay. Goodbye.
Yeah, that's at the networking things. These are different.
Got ya. Okay.
Yeah. So I have a question. And we've got time for a couple more. My question is, how much have you worked with liquid hydrogen? Have you worked with liquid hydrogen with rockets previously?
Yeah, with rockets, we did a couple of projects, but they were minor projects. Instead, we are actually working right now with liquid hydrogen with this Italian institution that is trying to develop, as exactly as I mentioned, a portable test infrastructure for basically it's for valves and pumps.
Well, that's really
So,
exciting because there are so few people that work with liquid hydrogen, which is why I wanted to have you on. Because even if it might not be for the same use case, the knowledge and experience that you have with liquid hydrogen is so important. What are your biggest challenges with working with liquid hydrogen?
uh, I wouldn't. I actually, I don't see very huge challenges. I mean, on the testing infrastructure side, everything is very industrial and it has really been tested and validated in the past. So I guess the real challenges are for those guys like you that are developing the flight components, so where everything has to be very light, very very well engineered. On the ground segment, it's pretty standard engineering stuff. However, there's not so many people that do it.
Right. And how do you deal with boil off? I hear so many people that work with liquid hydrogen say that it's just like money evaporating away.
Hmm. Hmm.
How do you guys deal with that? Or are you just working with
Uh,
a small scale to where it doesn't affect you as much?
no, we work with big scales, so we have a boil off rate on this like the standard ISO container tanks, and up until now we just burn it in a flare stack. So yeah, it's wasted money, that's true. However, I know that there are a few projects, and we are part of one of them, to recover the boiled off hydrogen and condensate it back and put it back
Mm,
into the liquid tank. Yeah, I think it's a matter of cost versus benefits. I mean, the cost of wasting a little bit of hydrogen due to boil off is a certain amount of money. The cost of the equipment to condense back the boil off is another very bigger amount of money. So the two things must balance out.
I see. That makes a lot of sense. How close is that technology to being ready? The recovering of the hydrogen.
We are in, let's say, feasibility study.
Hmm.
It's possible that there is something out there that is already working. I mean, it's not something that I'm so well informed about. Uh, but we are just beginning working on that on our side at least.
Interesting. Yeah, let's definitely stay in communication about that. I don't know of any technology like that that exists either, but I know folks that would benefit from having that.
Hmm. Mhm.
Will, I see your hand. You can go ahead and turn your mic and camera on and ask your question.
Okay, can you hear me, see me? There you go.
Yep.
Yep.
Hi, Dennis, thank you very much. And I'm wondering, so your testing systems, you've aimed them at people who are doing rocketry, right?
Mhm.
So is there any big difference between testing in the three environments, which is close to the ground, lots of oxygen, upper atmosphere, very little oxygen, and outer space, no oxygen?
Yeah.
How does that affect your testing?
Yeah, there is a huge difference actually. So ground level, it's easy. You're already on the ground. If you want to test a high altitude conditions, so for example, what the second or third stage of a launcher would experience, then you have a system which is called high altitude test facility. It's basically an ejector. You fire the engine inside this ejector, and there are some shock waves that are created inside this. Imagine it as a big pipe with a converging, diverging profile. And these shock waves seal the exit of the nozzle from the outside environment, so you are able to achieve a very low pressure at the engine outlet. If you want to test also ignition in vacuum, then you need a vacuum chamber, and you need to put your engine with all the equipment, or at least as much of the equipment as possible, for example, the load cell for measuring the thrust, inside the vacuum chamber, and then you ignite the engine under vacuum. So it makes a big difference, very close to the engine itself. But for the fluidic system that is supplying the, say, liquid oxygen, liquid methane, or liquid hydrogen, or whatever, it doesn't make any difference at all.
Okay, thanks. And your equipment can test all three environments?
No, we are actually working only on ground testing. We have designed a custom-made high-altitude testing facility for our client, Avio, and they have used it on their engine. Basically, we have the experience to work with that kind of testing, but nobody asked for it because
Nope.
it's very
Nobody asked
costly.
yet. Nobody asked for
No,
it
nobody. Okay, no, nobody asked yet.
yet.
Okay,
We'll get there.
okay,
Thank you so much.
excellent.
Thanks so much for all the questions. Thank you so much, Dennis, for that fantastic presentation. I'm definitely keen to learn more about this recapturing hydrogen. Our next speaker, and like I said,
Thanks.
we're doing things a little bit differently today, and I'm very excited because we're kind of switching things up. So next up, we have PJ Callahan. As the technical lead of supply chain, Mr. Callahan leads component sourcing for CSH2 and supports all business functions, including project development, operational planning, and engineering. Prior to which is ClearSkiesH2 Hydrogen, by the way, he spent 4 years at the Center for Transportation and the Environment, where he led the development of NorCal Zero, the largest deployment of fuel cell trucks in North America, with Hyundai and First Element Fuel. He holds a bachelor's in mechanical engineering from MIT. PJ, the stage is all yours.
All right, thank you, Danielle. I'll just pull up my screen here. Sure. How's that?
Perfect.
Great. All right. Well, thank you very much, and thanks to the HYSKY team for having me on here today. This is my first HYSKY monthly webinar. Danielle just reached out to me a few months ago, and just now getting a chance to engage. So appreciate the opportunity to speak here today. I'm going to tell you all a little bit about what we're up to at ClearSkiesH Hydrogen, CSH2. So we're a startup focused on hydrogen refueling infrastructure for transportation applications. A little bit of background. I've spent the last 5 years in clean transportation, originally with a nonprofit CTE, where I focused on prototype development for heavy-duty vehicles. Apologies, my slides keep skipping ahead. Not quite sure why. There we go. I spent 4 years with CTE, focused on prototype development for heavy-duty commercial vehicles with a focus in hydrogen, in port and drayage applications. That's where I managed the NorCal Zero project as well, which was a project to deploy 30 Hyundai fuel cell electric trucks, Class 8 trucks, in revenue service out of the Port of Oakland, with at the time world's largest hydrogen refueling station for vehicles, built by First Element Fuel. And through my work at CTE, I saw that infrastructure was consistently the bottleneck in all of our hydrogen projects. Frequently the vehicle OEMs, the suppliers, kind of had everything integrated well and running smoothly on the vehicle side with the fuel cell integrations, but it was really the infrastructure that was holding us back from achieving meaningful deployments. Often that was due to long construction lead times and unreliable equipment. Fuel cost was obviously contributing to that as well. And as I was seeing this, I reconnected with our co-founder Anthony Koo and Jimmy Lee, and crossed paths with them, and they together have decades of refueling experience with hydrogen and bringing commercial products to market. So these guys, along with our principal engineer Edward Yoon, had previously worked for a company called Nice America, where they built a really successful hydrogen refueler, which was unfortunately cut short due to geopolitical tensions between U.S. and China in 2022. But they were kind of watching the market evolve and decided they had some more designs that they thought could play in the space. So they continued to be active and co-founded CSH2 in 2024 with the goal of reducing fuel costs and unlocking scale in the hydrogen sector. So before I dive into our material, I want to take a few slides to set the stage for a discussion around infrastructure. As I'm sure many of you are aware, there are several different ways to store hydrogen on board a vehicle or on board an aircraft at different densities, each with unique infrastructure considerations. So this chart here just kind of shows simplistically the density of hydrogen stored along with the pressure profile. So I'm going to kind of step through this backwards. Here you have number 5, just H35, 350 bar hydrogen. And then if you double that pressure, you have H70, 700 bar hydrogen at 40 kilograms per cubic meter. And then if you cool that H35 hydrogen down to low temps, you'll get cryocompressed, which I think a previous company, Vern, who presented on these webinars in the past, is working on developing. You can get really high density, 72 kilograms per cubic meter out of cryocompressed hydrogen. Then if you just further cool your hydrogen and liquefy it, you can use either liquid or subcooled liquid, which is just liquid stored with a little bit of pressure to keep the boiling point low and allow the hydrogen to stay as a liquid form a little bit longer on board the vehicle. So those are kind of the 5 main storage methods that we see. The decision for which state to use is really driven by the demands of the vehicle and comes with trade-offs for range and carrying capacity and payload. So here's just a few examples of different vehicles we've seen using these different densities. So in the transit market, where a lot of our background and experience comes from in the on-road sector, urban transit buses tend to use H35. They can accomplish their duty cycle about 300 miles with 36 kilograms of H35 hydrogen stored on board the roof racks. There's plenty of space available, so it works well for that application, and they don't have to bother with the additional energy required to compress the hydrogen to 700 bar. So it's the most cost-effective means of using hydrogen for that
PJ,
application.
I'm so sorry to cut in, but I have a quick question.
Yes.
Because I haven't heard this before. When you're saying H35 and H70, are you just meaning hydrogen at 35 pressure up and 70 megapascals?
Yes, that's exactly right. Sorry, that's
Okay.
H35 is sort of industry standard for 35 megapascals. 350 bar, we'll also refer to it as 350 bar, and then H70 is 70 megapascals, 700 bar.
Okay, thank you. I learned something new. I never knew. That's how you said it. Thanks.
Yeah, sorry about that. We're jumping right in there. So H70, 700 bar is used in a lot of heavier duty applications, also a lot of passenger vehicles due to the space constraint. But in the heavy duty applications, so the Hyundai trucks we deployed and a lot of the other OEMs working on drayage applications will use H70 for density considerations to reach ranges somewhere around 450 to 500 miles where they currently sit. To achieve higher density, longer range, Vern's working on cryocompressed hydrogen along with some other companies. You can also use subcooled liquid hydrogen, as companies like Zero Avia are doing. So not necessarily, prescribing these types of densities for these applications some of what we're seeing in some of these heavier duty applications. So each of these methods are going to come with a unique infrastructure requirement. So gaseous-based systems, while they're fairly simple, can be somewhat limited in scale and cost, and they're really prone to reliability issues, but they generally work well at small scales today. So a lot of the smaller deployments will use gaseous tube trailers, just delivering high-pressure gas either at 520 bar or 900 bar, depending on how it's needed in the vehicle. If it's H35, it'll be on a trailer at 520 bar, so you can pressure fill with the difference. And then H70, you'll use 900 bar with the same concept. Just drop those off as a tube trailer and then fill into your vehicles from there, which is great and can work and is fairly reliable for low volumes, but for higher volumes, the delivery costs of going back and forth tends to be fairly prohibitive for anything more than a couple of vehicles. You can also use on-site generation if you have access to power or natural gas using either electrolysis or SMR. But typically, a lot of fleet operators who maybe own their station equipment don't necessarily want to be in the business of also generating their own fuel. So this can be a little bit complicated, adding an additional piece of equipment for them. Third option would just be pipeline, which requires a lot of capital infrastructure and investment. So we're not really there yet, but these are sort of the feasible operations. And then from there, you'll use gas compressors, which tend to be fairly energy intensive and unreliable, as I mentioned, into cascade tubes. From there, because of the heat of expansion of hydrogen as it goes into the vehicle, you have to use refrigeration to condition the hydrogen to minus 40 C before it can be filled in the vehicles. That's just to prevent over-temping on the tanks on board the vehicle themselves. So most of the systems today will use a refrigeration unit downstream of the cascade system to refill the vehicle. Then you can go to liquid if you can justify it with enough scale of your vehicle. So if you're above 2, 3, 4 vehicles in your deployment, you can go towards liquid. Liquid to gas is a really common way to reduce those delivery costs if you've got larger demand, say a couple hundred kilograms per day. So one of the legacy designs at the top here was basically just to deliver the liquid into a cryo tank, an on-site cryo tank, use an ambient vaporizer, and then to gasify the hydrogen and then compress it. Then basically the rest of your equipment chain looks very similar to what I just presented. This was, again, fairly energy intensive, and you had the benefits of the delivery of the hydrogen, but then everything else looked pretty much the same. So the unreliability issues and the energy intensity was roughly similar. Some of the newer station designs are moving towards using cryopumps directly. So instead of using high pressure gas compressors, they're using high pressure cryopumps to take it directly from a liquid into a high pressure gas to refill the cascade tubes, and then essentially similar design from there. Our co-founders pioneered another technique which helped eliminate the cascade system in refrigeration called direct fill architecture, taking the hydrogen directly from the cryo tank as a liquid, pumping it up to pressure, running it through a vaporizer actually to warm it up because the outlet of the cryopump is still relatively cold. So warming it up to minus 40 C where it can be dispensed into the vehicle safely within the pressure limits or temperature limits of the tanks. And then lastly, for cryocompressed and subcooled liquid, the chain looks fairly similar, even though they use a different type of pump. So you take the liquid hydrogen and pump it either with a high flow pump in the cases of subcooled liquid or a high pressure pump for CCH2. The outlet of that pump does not need to go through a vaporizer necessarily because you're using a cold high pressure storage mechanism in the case of CCH2. Then finally, we here at CSH2 are developing a cryopump and integrated refueling module that can fuel H35, H70, or CCH2 with the direct fill architecture. So this really dramatically simplifies the station, allows us to shrink the footprint and the capital costs associated. So getting rid of the cascade tubes and the refrigeration unit by doing a direct blend of the hydrogen stream for outlet of the cryopump and downstream of the vaporizer to achieve our temperatures can help us really simplify the station design and the controls. So really the key point here is that we think it's important to consider the infrastructure piece in addition to the end use, as the equipment is going to be a big driver of the overall TCO and effective fuel costs, as you've seen with all the different types of configurations. As I mentioned, scaling the offtake for hydrogen has always been really challenging, largely due to these fuel costs. So right now, many of the small fleets are using distributed gas in the form of tube trailers. When we would set up prototype demos back with CT, that's often how we would run things. If it's 1 or 2 vehicles, you would get a tube trailer and just dispense that right into the vehicle, or you can use a compressor as well to squeeze a little bit more out of that tube trailer. But really, it's small scale levels of equipment, and it gets really expensive once you start looking at getting a delivery of these trailers every single day to keep your fleet running. So to give you a sense of scale, one of these tube trailers can hold about a ton of hydrogen. So that's enough for a few vehicles to run per day. But if you want to achieve more meaningful levels of scale, you're going to need liquid, which is 4 times the amount for each load. So the tanks carrying liquid can carry 4 tons instead. So you're effectively cutting your delivery costs by 4 by using liquid. And we see liquid as really kind of the stepping stone into pipeline gas eventually. So in order to justify the build out of pipeline gas infrastructure, we need to achieve meaningful levels of deployment in meaningful industry scale on the vehicle side, which we think liquid is really the key for, sort of sitting right in the middle between tube trailers and the pipeline infrastructure down the road. I already heard it earlier in the webinar coming up there in the Q&A, but one of the core issues commonly cited with liquid is the boil off, which leads to the venting of the product and loss of fuel, obviously. So that's going to dramatically increase your fuel costs. And it's really critical here to maintain the condition of the hydrogen as a liquid to avoid it, which can be challenging. So we've kind of distilled this down to 4 main sources of boil off that we see on the station side. The first occurs in the delivery of the hydrogen. So hydrogen will come in as a liquid on board a tanker, mostly full of liquid. In order to deliver it into the cryo tank, they use a process called transfilling, where basically the liquid gets vented off into a pressure building loop that builds gaseous pressure in the liquid tank to create a pressure differential to then fuel and flow the hydrogen from the tanker into the on-site cryo tank. So all that hydrogen that gets vented as a liquid to build that pressure is now effectively lost product that you're not able to use as a liquid for your cryopump. So that's one main source, and that can contribute quite a bit. We think somewhere in the neighborhood 20-30% of the total boil off that we see in the station is due to this delivery loss, depending on a number of factors, obviously. The second is static heat loss, so NER into the tank, normal evaporation rate caused by just imperfect insulation. No insulation is 100% perfect, so imperfect insulation in the tank from causing heat leak into your liquid is going to over time boil off some of that liquid and create some gas inside that cryo tank, which eventually has to be vented off through pressure safety loops. And then the third and fourth mechanisms are directly related to the pump operations itself. So the pump cool down, you've got to imagine like a lot of relatively warm metal that needs to be cooled down in order to start flowing your liquid through. Otherwise, it'll just immediately vaporize, and you'll be pumping liquid, or you'll be pumping gas instead, and effectively creating cavitation in your pump, which is going to wear things out pretty quickly. So you need to cool down the pump and all the associated components to make sure that it's not vaporizing, causing cavitation. And then the fourth is due to pump operation. So actually, a lot of the cryopumps now are being used, repurposed cryopumps from LNG industry, and they're not really well built and purpose-built designed for hydrogen. So it leads to a lot of losses in that process as well. So collectively, we're estimating a significant amount of hydrogen is lost, between 0.3 to a full kilogram per kilogram dispensed. So almost 50% of the fuel that's coming in is being lost through one of these 4 mechanisms. And that's going to depend somewhat on the utilization of the station, but effectively that's why you have such a large range. But this is a significant amount of fuel, and this is really driving fuel costs up for the liquid hydrogen market. So we at CSH2, as I mentioned, are developing technology to attack some of these core issues of boil off with a purpose-built clean sheet cryopump design, going after mechanisms 3 and 4 initially that are due to the cool down and operation of the pump itself. So we've designed a purpose-built cryopump specifically for operation with liquid hydrogen. It's designed to be low cost and very easy to maintain to overcome some of the limitations of current pumps. So significant reduction in CapEx and OpEx. Combine this with our direct fill architecture approach, and we can dramatically reduce the station footprint, going from a concrete pad that would normally take up 100 by 50 feet or so. We can shrink all that equipment down into a 20-foot shipping container. This is also dramatically going to improve our station flexibility and cut down on construction timelines. and makes it possible to establish a networked approach of standardized fueling stations to build out the stations. And with this approach, we think we can get a full station down from, between 20 and 25 million, as we've seen some stations creeping up into, down to about 5 to 10 million. There's a significant reduction in capital expenditure when you eliminate the cascade refueling, the refrigeration units, and purpose build your cryopump. There's quite a bit of savings we can see. And then finally, we're going after the transit and trucking markets initially, as they have the highest TRL on the vehicle side, with operators very eager to adopt, especially with the regulations in California for transit operators. But we are very eager to explore other applications as well. So we can fill those tube trailers that I mentioned that can support small scale demos in 900 bar or 500 bar. And our equipment's very effective for doing that. You can tap into the existing liquid hydrogen infrastructure to refill those trailers, and then support applications where they may not have space or power for a permanent station, but you can set up some of these tube trailers and do some initial demos of vehicles or demos of other types of equipment. And then we can also refill, as I mentioned, the CCH2 vessels directly as well. So we're excited to explore some of these emerging markets for H2 delivery. If there's any opportunity or interest in follow-up and discussions for partnership in any of these applications, we'd be happy to connect. So that's all I had. Thanks so much, and happy to address any questions.
Thanks so much, PJ. That was fantastic. I have a quick question. Mike, I'll call on you in just a minute. Can you go back to the previous slide? You probably explained this, but what is CCH2 and CSH2?
CSH2, ClearSkiesH2 hydrogen, is
Oh.
just short for our
Oh
company
yeah,
name.
I said that in your bio.
Yep, CCH2. If I go back to the original slide here, it's probably the easiest way to explain it. CCH2 stands for cryocompressed hydrogen.
Got it.
So you see it referred to, it's number 3, cryocompressed hydrogen, high density form of hydrogen that's very cold. So 54 Kelvin, and high pressure, stored at 350 megapascals or
Which is
300 to
what
350.
Vern
So
is working on, right?
exactly, yes,
And
yeah.
are you
Companies
guys
like
partnered
Vern.
with them? I noticed they're were in one of those pictures.
I'm sorry.
Are you all partnered with them? I thought I saw them in one of your slides.
We are exploring opportunities with them, yeah, to directly fill from our pump, the outlet of our pump, into their vessels, yeah.
Very cool. Mike, would you like to turn your mic and camera on and ask your question?
Yep, mic is on. So yeah, so Mike Hirschberg from H2 Advisors, and really exciting to have you here with HYSKY Society. I hope you do take advantage of all the networking and collaboration efforts that HYSKY offers. I'm also on an SAE committee, hydrogen refueling at airports, that you might be interested. Zero Avi is a big player in that. So if you're interested in particularly knowing the requirements for refueling and interconnects and things like that, there's opportunity there. I'll put a couple links into the chat, and I'll reach out on LinkedIn if you want to get more information.
Yeah, that would be great. Thank you, Mike. Like I said, aviation is something that we're starting to get some understanding of, and trying to dip our toes into, with a focus on the on-road applications, but certainly want to learn more and engage. So yeah, I would appreciate that. And I think Danielle, you'll pass around my contact information and the slides and whatnot, so we'll be able to connect.
And H2 is definitely the place to learn about everything going on in aviation, the
HYSKY,
aviation
you mean?
world. HYSKY is definitely
You
the
said
place to
H2,
get
but
Right.
yeah.
No, sorry, thanks.
No worries. Yeah, and it's so important that we work with folks like you, PJ, because what the transit industry has done, you've got loads of learnings that we can learn from. We as a collective for aviation, hydrogen aviation, collectively know what we need on board the aircraft and what needs to be at the airport. But people like you, PJ, have the experience and the expertise to help us get there. All right, I see next we have a question from Tom. Tom, would you like to turn your mic on and ask your question?
Yeah, I didn't realize that the speaker was, was kind of new to aviation, but let me throw my question out there. mostly what you shown so far is refueling vehicles at ground level. Uh, and I think you alluded to it, Danielle, already. When it comes to aviation, and you loaded, let's say, a hydrogen tank on board an aircraft, you'll be flying at pretty high altitude where pressure conditions are going to be a little slightly different. So, any words of wisdom so far as ideas on storage on board the aircraft once you have you gotten done the refueling?
Hmm. Um, it's not something that we spend a lot of time on, but if you have a large pressure differential on ground and then you go up into the sky, that's only going to amplify, right? So you got to make sure to fill your vessel to the appropriate pressure at the ground level to where it's still rated for that pressure differential at the higher levels. So you have to select your tank accordingly to make sure that you can achieve the right density, right? Because these are all rated for 700 bar tanks are rated for, say, 1,000 bar working pressure. But if you fill it to 700 bar on the ground, I mean, I don't know the math exactly off the top of my head, but if you fill it to 700 bar on the ground, are you going to overcome that when you're up at 35,000 feet? So you might not be able to fill it to the full density. Well, now that density is going to affect the range of the vehicle and all those types of things. So you have to be, considering of all those factors. So there are, uh, you know, other companies working on, like I mentioned, Vern, working on the storage systems with the carbon fiber reinforced high pressure tanks. Those might be a good option for that. The liquid tanks tend to be low pressure rated, they tend to be very sensitive to pressure differentials. So they're typically only rated for up to like 20, 25 bar maximum before you run into issues with cracking of the tanks. So I know that there are companies like Zero Avia, Universal Hydrogen was another one working on the storage systems for altitude. So I don't know exactly what they've done to overcome that, but that's a key consideration with liquid hydrogen. So yeah, kind of taking that into account, right?
Okay, thank you very much.
Thank you for the question. Sarah, I'll come to you next, but first I want to ask another question to PJ. PJ, could you go back a couple more slides? I want to make sure I understood something that you said. Keep going back. It's the one where you talk about the pipelines.
Oh, here?
Yeah. Okay. So you said you see the liquid tanker. Now, mind you, I'm multitasking over here and also letting people in from the waiting room. So I want to make sure I heard you correctly. But like the liquid tanker was sort of like an intermediary step to get towards pipeline. If I understood that correctly, do you guys see hydrogen being eventually piped? And if yes, would that be existing pipelines sleeved? Would that be new pipelines? What is the sort of outlook on what do you see, how hydrogen will eventually be shipped at scale?
Yeah, so as I mentioned, right now, a lot of it's happening at smaller scale with 2 trailer deliveries of high pressure gas. That's a really effective, cost-effective way for small scale deployments. It's very simple, relatively simple. But as soon as you get past, say, a few dozen vehicles, it becomes very difficult in a single deployment. You have a lot of deliveries of gas. It becomes very costly, and the infrastructure doesn't really pencil out. So that's where liquid becomes a much more dense way to transport and much more effective way to transport. It also has lower on-site energy costs if you're comparing compressors to a cryopump. They're just a lot more efficient. So we see liquid as kind of a way to achieve some levels of scale. We already have 3 liquefiers online, serving the California transportation market with others in BC planned. And I think there's, Plug Power just opened up several in the Southeast. So there's a lot of existing liquid infrastructure that can be tapped into to serve these applications and to move us towards, higher scales. Pipeline, I think, is something that is really only justified once you've shown that the markets are really there and are taking off. So right now, we're still working on getting out deployments of transit buses. We're in the, I think, hundreds to thousands still. Drayage trucks, we're still in the, scale of tens, even in California when it comes to hydrogen. So I think we've got to get meaningful levels of vehicle scale to justify pipeline build outs before anybody's going to commit the capital cost, whether it's retrofitting or new pipelines, before anybody's going to commit the capital cost. do that. I know there's a lot of discussion around pipeline infrastructure, particularly in California, within the Arches Hydrogen Hub, and they're looking at some of the studies that were done. SoCalGas, as a utility, and has done a lot of studies around hydrogen blending. I understand there's a lot of challenges with that, particularly embrittlement of the existing infrastructure. So, they have to be, sort of sleeved, as you mentioned, or retrofitted to account for higher levels of blending, and then you have to extract that hydrogen on the back end. So, as far as blended versus new, I don't think we've really decided that yet. But I think there's a lot of challenges with blending. So, it could go towards building new pipeline infrastructure. I'm not an expert on that, but certainly we need pipelines to achieve the types of costs that you're seeing here. So right now, liquid at the gate is somewhere between $6 and $8 per kilogram, which is actually pretty good. But to give you a sense of comparison, we need the dispense cost for hydrogen to be about $5 to $6 to reach diesel parity. So if you're already paying $6 just for your liquid, that doesn't even factor in all the transport costs and all the equipment costs and energy costs on site to fuel it. So you're talking about $12, $15 per kilogram. If we can get liquid down to, say $2 to $3, then you get more competitive, but that's going to be harder. So then we look at pipeline where, effectively, if you can build them out, you can transport a lot more hydrogen very, very cheaply without those delivery costs. And so now we're looking at, dollar. When you see the targets from DOE talking about, $1 per kilogram of hydrogen, it's likely going to have to be sort of piped as the most effective way to move it.
Very interesting. Yeah, the trick is getting that offtake to scale.
Exactly.
Okay, next, Sarah, you want to unmute and ask PJ your question?
Yeah, when you were showing the I guess the first set of processes to convert, yes,
Yeah.
that one. So I assume that from no, the previous one.
Oh,
So I
sorry.
assume that the bottom one is the least expensive of all of them, or are there any major production cost differences between any of these three methods?
Yeah, definitely. So the simpler the station, the cheaper it'll be from a capital perspective. So the first design is really a legacy design that was sort of before we had developed a lot of our cryopumps. This is what a lot of stations were looking like, where you just vaporize the hydrogen coming out of the cryo tank and then you put it into a compressor. The
Right.
compressors are very expensive and to operate and can be somewhat unreliable for larger scale. So that's something that's, there's a lot of work going into developing better hydrogen compressors. And as we get into pipeline, I think that market will evolve as well. But you could see all the amount of equipment here. It does make this quite expensive to operate. The second option moves towards a cryopump, which is going to be a little bit more effective for liquid itself. But if the key driver here, the cost is the cascade storage and the refrigeration units, which take up a lot of space. The storage tanks take up a lot of space. Which is just additional land costs. And then the refrigeration is very costly and can also be pretty unreliable from what we're seeing. So if you take those out using some smart controls of your cryopump, if you're smart about the way that you're using the discharge from your cryopump, you can blend the streams coming out of the vaporizer and the pump itself to use some of the cooling duty of the hydrogen coming out of the cryopump. So that's just a process design change instead of an equipment change, which is going to be a little bit cheaper. So that'll reduce the effective fueling costs as well. So this is a newer technique that I mentioned our co-founders pioneered at the last company. We don't see a lot of existing infrastructure that utilizes this type of technique yet. But that's one technique that we're integrating that we think is going to dramatically shrink the station cost and the footprint.
Yeah, it would be helpful if you were presenting it to a potential customer, right? To show I mean, an estimate of the cost or footprint or whatnot, just so that it looks kind of in your face. But you were looking for partners to test, right? And I occasionally have come across some things on grants.gov that are meant to be for communities to request. And some of them obviously are, to reduce global warming and whatnot. So, I mean, that might be a potential way for you to find which city, right? Which city is actually pursuing this, and maybe it'll be easier for you to locate a partner within that city.
Yeah, that would be great. Yeah, we do have grants.gov login, and we'll continue to check that. We keep an eye on the activities, and particularly in California.
Yeah.
So yeah, I did simplify the slides a little bit, but to give you a little sense of kind of where we're at, we're completing our first hydrogen trials over the next couple of weeks, and then moving into a commercial demo with a truck partner early next year. So we do have our initial demos lined up, and then we're looking for market entry and commercial partnerships later in the back half of 2026. So really, I mean, as I'm sure you're aware, the planning time for that starts now. So definitely appreciate the advice on grants.gov, and we'll keep an eye out.
Yeah. Thanks.
Thank you.
Thanks so much for all the questions. PJ, excellent presentation. There are a couple more questions we don't have time to get to, but feel free to answer them in the chat.
Great.
And we are going to move on to our next speaker. Let me just get
Thank you
my
very much.
slide, my screen sharing. Okay, great. So next up we have Diego Moreno. Diego is the manager of hydrogen and low carbon fuels at Edmonton International Airport and the program director for infrastructure at the Edmonton Regional Hydrogen Hub. He leads key initiatives in advancing hydrogen deployment in the region. Diego holds a PhD in chemical engineering from the University of Calgary, specializing in catalytic clean hydrogen production. With over 14 years of experience in the downstream energy sector, he has held technical and academic roles at Hatch, Suncor, Ecopetrol, I hope I'm saying that right, and multiple universities in Canada and Colombia. Diego, I am honored to have you. I think you are our first actual airport that has hydrogen at their airport. So without further ado, Diego, the stage is all yours.
Yeah, thank you very much. Good morning here. Good morning, good afternoon in some regions. Thank you very much. So good to see from my previous partner here that some of the company that they are working with. So as well, we have a beautiful relationship with them. Yeah, I'm happy to start with this presentation. Thank you very much for everything. Something they look so beautiful on the paper, but believe me, to bring them to the reality is another thing. So happy to share the experiences that we have having around. So let me share right now. Okay, 1 second. Okay, perfect. This one. Perfect. So please correct me if everyone can see.
Yep. Could you go to full screen?
Perfect.
Or
Yeah, perfect.
presentation? Yeah, perfect. Thank you.
Okay, perfect. So thank you very much. So I am very glad to present you here the information that about the show that we have been doing for a while. So I represent Edmonton International Airport, and specifically the hydrogen hub that is one of the main pilots that we have been working with. And I'm very honored to be supporting from the beginning of this project with as well with the huge mandate from our executive leaders. So this is the question. The first picture that we can see here is the Edmonton area, and Edmonton is a very unique area here in Canada. And I would say that we are very gifted by nature. And I would like to start with why hydrogen is very important in this region. So first of all, I would like to share this cover of this magazine that we presented like 1 year ago, I would say. So we're definitely how the hydrogen is very embedded into our ecosystem as well, because for us it's very important because we are very unique in this area because we face low temperature, especially from December to April, I would say. And mainly because Edmonton is the Canada first hydrogen hub. So here, 60% of Canadian hydrogen is produced in Edmonton. That means around 2.4 million tons per year. This is ideal. But we have been using, especially from the world that I came from, that is oil and gas industry, we have been using hydrogen production since 50 years ago with the big oil producer that we have around. But right now we need to get into the clean hydrogen. And that changed everything because the cost of clean hydrogen is totally different from the gray color that we have right now. And don't forget that as an airport or an institution, so we have mandates in order to decarbonize our facilities and our operations. So let's call scope number 1, 2, or 3. I'm pretty sure that plenty of you are very familiar with this. So basically, we work here as a catalyst, a bridge between the production, adoption, I would say, all the supply chains drivers. So we are the biggest airport in terms of land. That is very important. As you know, a lot of the airport, they are already surrounded by the city itself. So it's very difficult to build something into or around them. So we have around 7,000 of acres in order to be built. We offer feature to technologies companies. So we have partnership with plenty of them that they come here to de-risk their operations. And as well, we have the huge support here of our provincial government and federal government. So the political stability that we have in Canada, and actually both government, either provincial and federal, they are very aligned in one thing: hydrogen production and hydrogen is in adoption as well. And it's good to have this kind of incentives. So we are bringing companies to our land. So we are very happy to have them around. And before to start, so just to mention, Edmonton, we face temperature when it's winter here is so far different than California. So in California, you're gonna have a bunch of EV cars. They were so beautiful there. Lowest temperature around 10 Celsius degrees. But here, when we talk about real winters, is when we face minus 42 Celsius degrees, minus 45, minus 40. That means that an EV car that is working at below minus 13 Celsius degrees. So basically they don't work. The battery are drained. That is why hydrogen is very popular here, and we are very close to the main hydrogen production units. That at the end is where the cost is going to go down. So we propose, and from the strategic point of view, so definitely to start to adopt hydrogen. For example, we already started, actually, one of our latest project that we started is the adoption of a hydrogen dual fuel vehicle. So to replace a diesel vehicle, heavy duty vehicle that is specific for aviation called Snow Sweeper. Because here our winters, they last around 5 months. And this vehicle need to be working all the time, 24/7. That means that we can replace diesel engine by a mixture of diesel and hydrogen. If the supply of the hydrogen isn't around, so they could enter to work with diesel. That is very suitable. Right now, the airport as well, we have some fleet of vehicles based on hydrogen, and we have a temporary hydrogen refueling station that I'm going to show you. So this is a picture of our airport in our control tower. So YEC support mobility. So we have as well, I mean, all of us, we know that the aircraft, they would be the final objective to tackle, but we need to be honest and realistic. So that is a little bit further on the road. Of course, we are working toward that objective as well with some partnership that we have with these companies like Avia. We like to move ahead in everything that we have with them. But to be realistic, we need to start with the technology that we have right now at commercial level. So given that fact, so we have a premium partnership with Toyota, and as well, we acquired some vehicles from Hyundai, and we have been using fuel cell vehicles to decarbonize our fleet. So in total, we have 12 vehicles between the Toyota and the Hyundai one. The Hyundai actually right now is working with the airside inspection vehicles, and this is driving that the decarbonization objectives are going to aligning, specifically from the scope number 1 in order to go down. As well, we have our hydrogen refueling station. This is a temporary one with a partnership that we have with Air Product, a very reliable hydrogen production technology provider that we have around. And that is something very important. We have seen, and we know that there are a bunch of very cool technologies that they are around, but they are in low TRL. And as you know, an airport, they never can fail. That means that reliability is everything for us. So we need to have a plan A, B, C, D. You never are going to see an airport that is going to shut down because the plan A failed. So for us, we need to secure that their hydrogen supply is going to be constant and totally reliable. That's why we have this partnership with AP, and they have been very stable in terms of supplying the hydrogen for us. So, of course, we are identifying as well what have been the learning curve, and we are working on other projects in order to supply hydrogen as well from the land itself. So with this hydrogen, that is gaseous hydrogen, that comes in cascade mode. It's not the ideal one, as you know. So we have very interesting project that we would like to get even more. But realistically, is what we have right now. As well as we know, liquid hydrogen is very expensive these days. And if we don't have a stable demand, that is the problem that we have with mobility. So we need to as well to minimize the risk and the financial risk as well, and minimize the cost. That is why while the adoption is increasing, we are working with gaseous. In the project that I mentioned from the beginning, so the retrofitting of the snow sweeper, so these one are the vehicles. So we started with a project that it was, we applied to a grant from Alberta Innovates, that is from an institution from the government that they support the hydrogen adoption, distribution, and production. So we got a grant with them, and we are working with a partner in order to develop technology to retrofit the engines. So the hydrogen tanks are going to be located in this area, and that is the beauty of these vehicles, that they have enough space in order to allocate the hydrogen around of them. So this project started in April. Right now, we're in the first milestone. The plan is to start the project to run the vehicles probably for the winter of November, October. So let's see how everything is continuing, but we are working pretty well. We are aligned with the schedule, and we haven't had any problems. And as well, we guarantee the hydrogen supply. That is the main barrier that plenty of companies have, that they don't have a stable hydrogen supply in the area. So we have in situ hydrogen feed for these vehicles. So why is this important as well? Because hydrogen is one of the cornerstone later on for the SAF production. So one of the several the technologies for SAF production, we know that SAF is a very tricky point and it's very expensive. The cost of SAF of one sustainable aviation fuel, so it could be 3 times the cost of the regular jet fuel. And here in the area, so we would like to promote that SAF production with clean hydrogen. So that is why for us it's very important, because we wouldn't need to retrofit the vehicles. And as well, we are very keen in order to expand the airlines operations, especially with Europe. That is where they have more certified mandates. So this is something that we are working on as well, in order to incentivize as well the hydrogen production from the provincial government as well. So SAF is especially important for us, and hydrogen is crucial there. Recently as well, so the airport joins a consortium called H2 Can Fly. This is a consortium, a pan-Canadian consortium where several companies like Airbus and NRCan, that is the National Resources Canada Institution, so about science. So it's in order to create, and other very important organization in the area. So it's in order to promote the research and the adoption of hydrogen and create projects related to hydrogen adoption, either for aircraft, engines, or ground support operation, anything related with hydrogen. So we are starting this consortium, and we're very happy to have be with them around in order to promote even though more this ecosystem. Collaboration is key for everyone here, so definitely we need to work together. So we consider us as a catalyst. So we have several NDAs with very hydrogen organization, manufacturer. As well, we are working with several institutions from the Aviation Authority. So this is a complete new world to everyone, believe me. So 2 years ago, no one knows about this. Even right now, we are working with the local authority created with jurisdiction, and they don't know. So this is a job that we are doing together, and it's good to be in this race. So as well, we are working with the SAE, that we have some members here, very happy to belong to this organization. And we are more than happy to share and to adopt any kind of hydrogen production technology from the reliability point of view. Yeah, thank you very much for this opportunity. I'm happy to listen to your questions.
Thank you, Diego. That was fantastic. Can you go back one slide?
Oh, sorry, let me go back.
No worries. I just have a quick question. I'm wondering if that SAE group was the same one that Mike was talking about.
I think so. Yeah, Ionic-1. Yeah, I think so.
Yes, it
AE5C.
is.
Yeah.
And then is the Airport Infrastructure Expert Advisory Council something different?
Yes, it is.
Yeah. That is the and even we have other one that I don't remember the name, but yeah, we are there.
Small world.
And-
Okay, very
Yeah.
cool. Also
and-
excited to see that you're part of H2 Fly. We have a lot of friends over there. So yes, it is very much a small world, and there aren't that many of us. So anybody that's new in this space, don't worry. It won't take you that long to catch up because we are at the very, very early phases. Um, what are your, I guess, what are your plans for 2026 to 2030? Where do you see Edmonton going?
Right now, to everyone, it's not as a secret that definitely after the election of 2024, so what happened in 2025, so this hydrogen world, the saying that the renewable clean energy has decelerated a little bit, not a little bit, a lot, I would say. So plenty of the project and the momentum still is there, but not with the same speed that it was before. But as well, it's allowing us to think how realistic is and not the hyper movement that we used to have. And this is something that we have been very, from my arrival, so I have 2 years with this organization. So it's as well, I support the Edmonton Region Hydrogen Hub because we are working together until where the airport fail or not fail is the limit. So the Edmonton Region Hydrogen Hub enters because this is a job work together. We cannot do it alone. We need to work with the city itself because it's a full ecosystem. We are not, all the time I say, we're not working here just for the airport itself. We are working for the full city, I would say, or the surrounding areas, because we need to create the demand. So for our side, so definitely we are working in order to explore hydrogen production to deliver this hydrogen. It need to be a low-cost hydrogen. Right now, we have experienced that the cost is extremely high. For no one, that is a secret. And my colleague here mentioned the transportation cost of gaseous one is not ideal, believe me, at all. But it is what it is right now. So, but for us, because this is something that falls under the provincial needs or the provincial strength that we have, because here we are the main natural gas producer. So in order to catalyze, to leverage that hydrogen production that we have internally in the province, so is to convert and add a value to the natural gas. So that is one, and we are not married with any kind of color of hydrogen. This is something, even when I have been in USA, in Houston, on events, or with California, when we're talking, this is not a problem of color of hydrogen. We need to start with something. Just start it. That is the main problem. We have seen that plenty of companies, they are working and thinking about, oh yeah, we're gonna have this cool hydrogen technology 2040. Yeah, but we need to start with something right now. And believe me, there weren't before SOPs, manuals for fueling, for hydrogen. So no one even not an airport. And some thing that we have heard is that, no, the airports, some of them, they are independent. That is true, but under certain level, because even though we need to follow regulation from the specific localization where we are. So we need, and they don't know. So they don't know. And even, for example, if we want to store the heavy duty vehicles with hydrogen in the tanks, for example, thousands of us, we haven't thought that, okay, we need to develop a code, a building code for this in order to store this kind of vehicles. And that costs money, the evaluation, and no one knows. So these kind of things are the things that we already started, because we are envisioning that for the near future, we want to be ready when the price go down. And we are working together with the region as well. So we have planned that at our partner Air Product, they're gonna come probably in 1 year with a blue hydrogen facility, commercial level. So 1,000 of tons per year. So we're gonna have clean hydrogen around. But as well, we are open, we are agnostic of colors, because we need to start to incentivize the demand. So we are open to green, to turquoise hydrogen. So why? Because we need, whenever the demand is a little bit stable, we reach the plateau, or at least we have some data. Okay, the other huge one would come. For example, you were talking about pipelines. Right now, we are working as well in order because that comes from regulations, and at the end, this falls under the decision that the politician they makes, and they don't know, and they are afraid. Like 90%, even our operators in the airport at the beginning, oh no, hydrogen, no, I'm not going to touch that. So we need something. So we need to.
Mike and I call it the hydrogen. We call it Hindenburg syndrome.
Exactly, that happens. So we need to create the awareness, but as well we need with the regular population, but as well with the politician from the regulatory point of view, because we need to incentivize, for example, we would love to receive hydrogen by pipeline, and we are very rich here in Alberta, and that would be through regular, 5% or up to 20%, but that is a gradual work that we need to start to do it. So basically, just to mention, the airport is part of the second phase of the hydrogen, the city hydrogen hub, Edmonton hydrogen hub, and is a co-founder, not co-founder, it's funding along with other 4 partners. So it's crucial that the airport get into the equation as well with the general ecosystem that is surrendered, because that is going to attach and is going to leverage the offtake. Because that is the problem that we have seen, that we have a bunch of hydrogen production, but no one is buying hydrogen. Why? Because it's so expensive. And especially here in Alberta, our cost of natural gas is super low. We have that advantage. So I would love to have hydrogen right now into my cogens, but the cost is so high. So we need to start with something. And so far from our side is with mobility sector. Is where we found we can have a, still is high, it's a premium cost related to to diesel, but when it's something that we can start to work with, and as well that requires that the airport itself take the decision, and as well it's very well connected with the region, I would say.
Yeah, I couldn't agree more. Right now, the color of the hydrogen does not really matter. It's a fact of like getting people exposed to hydrogen, used to hydrogen, with the knowledge that it will eventually go green. Similar to how we have electricity in our homes, and a lot of us aren't really aware or really care where that electricity came from or how it was produced. But now that we have electricity, we can easily add solar panels and wind turbines and things like that. But getting used to the electricity was the first step, and then we can go green after that. I want to open the floor for some questions. If you have a question, feel free to unmute your mic and ask Diego your question directly. I haven't really been looking at the chat, so if you did ask one in the chat, just go ahead and come on. Otherwise, I will just keep asking questions. Another thing I'll point out, and feel free to jump in if you have a question at any time, but another thing I'll point out, if you're curious about the logos behind Diego and the other speakers, you can get your logo on the background for as low as $250 a year, and your logo goes on all of our presentations, which are viewed by thousands of people because these go on our YouTube and our website. So join, you can do that at connect.HYSKY.org. Philip, hi, Philip. He's one of our VIP people. His logo's right behind Diego's head. FC Renew. You're up, Philip.
Great organization, and certainly area we want to see grow. And just in terms of kind of the longevity of the project at the airport, is there, where it sits now, is there a lot of resource intensive needs that it has where this slower kind of on-ramp timeline is still sustainable, or is it something that every day kind of brings it back up to a question of its fate?
Are you talking about the
just having hydrogen at the airport, period? Is it something that seems like it's going to continue forward in that next 5 years?
Oh yeah, that is a pretty good question, a very sensitive one, especially when we talk about budget.
Yeah.
So because it's not cheap at all, to be honest. But as well, it's a transitionary option that we have so far. And we want to take advantage of our huge land that we have around, the expertise that we have from several energy companies in our area. We are exploring to get into that market of hydrogen supply, I would say. This is something that we are working around. And as well for our, I would say that initially and the final objective, it could be, of course, for our own consumptions. Because when you want to find third-party of takers, that is the equation becomes very difficult. So we have been exploring this since a while. That is my role here. Let's wait what happens next year, if I can give you some other news.
Great
Thank you.
question. I also want to remind everybody that the H2 aircraft certification course starts next week, which is mind-blowing that it's already here. But next week we are launching a 3-week, 6-lecture, 12-hour aircraft certification course that goes through everything, existing frameworks. We've got EASA certified instructors, Transport Canada certified instructors, and folks that work closely with the FAA. So you'll definitely want to sign up for that. You can just go on our website to find that. We've got 2 minutes left. Does anybody want to ask a last minute question? Okay, I'll do the outro, but if you have a question, turn your camera and mic on before I end the call. I just want to send a huge thanks to Dennis, PJ, and Diego for this fabulous presentation. If you're a regular to these presentations, please put a 1 in the chat if you regularly attend HYSKY Monthly. Put a 1 in the chat. And then if you preferred this method better than previous presentations where we have multiple speakers speaking for shorter, put a yes or a no. Yes, you prefer this better. No, you like one speaker better. Mostly yeses, 1 no, mostly yeses, another no. So maybe we'll switch it up. It looks kind of like half and half. We wanted to try something new to see, do we like to have the really long deep dive into a company, or do we want to kind of break them up into shorter presentations? So maybe we'll switch it around here and there. Both. Yeah, I think both is going to be the way to go. Well, thanks again, everybody, for attending. Thanks again to all of our amazing speakers. You'll be able to find these on our website and our YouTube channel, and you'll be able to access the slides there. And everybody have an amazing week. Bye.